The last thing we are going to look at is the formation of multiple bonds, either double bonds or triple bonds, when we have atoms that are also using hybrid orbitals. Sometimes when we are forming our hybrid orbitals, we had extra leftover p orbitals that did not get thrown into our hybridization mix. Multiple bonds are formed from the overlap of unhybridized p orbitals. Those unhybridized p orbitals must contain electrons within them if we're going to form either double bonds or triple bonds. Use valence bond theory in hybridization to describe fully the bonding in ethene, C2H4. Let's start by drawing the structure for ethene. We're going to have carbon bonded to another carbon. Each carbon will have a single bond to two hydrogen atoms, and there will be a double bond in the middle of each carbon. So when we use valence bond theory, we're going to have to describe a double bond, and we're going to have to describe a single bond from each carbon to each hydrogen. If we just pick one of our carbons to represent a central atom, since there is no real central atom, we can describe the bonding to that carbon, and the bonding to the other carbon on the right will be identical. Let's start by writing out our electron configuration for carbon. We can use the shorthand notation, helium in brackets, 2s2, 2p2. And if we look at our orbital diagram, we have our 2s orbital and our 3 equal energy 2p orbitals. We're going to have 2 electrons in the 2s and 2 electrons in the 2p. So remember, it looks like carbon can form 2 bonds. But how many bonds is carbon actually forming in our structure for ethene? If we just use the boxed in blue carbon as our central atom, how many domains are around that carbon? How many bonds does it have to it? So it has one bond to hydrogen, another bond to the other hydrogen, and then it has a bond to this whole group, this whole CH2 group. So that carbon has 3 things around it. Therefore, we would say it is AX3, or its geometry is trigonal planar. It arranges itself so all the groups, the 3 groups, are spaced out 120 degrees apart, maximizing their distance between each of them. And so since carbon needs to form 3 bonds or 3 domains around it, we're going to have 3 equal energy hybrid orbitals. So first we can imagine taking one of our electrons and promoting it, so one electron from the 2s and promoting it up to the 2p. And when we hybridize, we're going to have to put 3 atomic orbitals into our mix in order to get out 3 new hybrid orbitals. So we'll mix in 1s and 2p's. We'll mix in those 3 atomic orbitals. And what we'll get out are 3 equal energy new hybrid orbitals. And we're going to name them based upon what we threw in. So they'll be called sp2. We'll repopulate them with the electrons that were in there before. And notice what we didn't throw into the mix. We didn't throw into the mix one of our 2p orbitals. So we still have another 2p unhybridized orbital. And it's important this time because there is an electron in that unhybridized orbital. So if we start by thinking about how we're going to draw this using valence bond theory, each of our carbons, and right now we're just focusing on the blue boxed in one, but each of them has 3 sp2 hybrid orbitals that are half filled and 1 half-filled unhybridized 2p orbital. Hydrogen is going to be bonding with, as we saw quite a few times before, hydrogen's electron configuration is just 1s1. So hydrogen will have a half-filled 1s orbital. It'll have 1 electron there. And so hydrogen can use that half-filled 1s orbital. It's not hybridized, it's just an atomic orbital that has a spherical shape. So if we draw our trigonal planar sp2 hybrid orbitals on carbon first, we're going to have them be 120 degrees apart, and carbon would essentially be in the middle of all of them. So sp2 hybrid orbitals will look a lot like a combination of S and P together. They're going to have about 66.6% P character and about 33.3% S character, just based upon the atomic orbitals that were used to create these hybrid orbitals. So that's one of our carbon atoms with its 3 sp2 hybrid orbitals, all spaced 120 degrees apart. And now the other carbon atom is going to have the exact same thing. So we'll draw another sp2 hybrid orbital on this carbon atom, and then the other 3 will get spaced apart appropriately. So those are our other sp2 hybrid orbitals on our second carbon atom that we didn't box in. So along the internuclear axis right here, we imagine our imaginary internuclear axis running along where the x-axis would be on a coordinate system. We can see that we have that direct orbital overlap between one sp2 hybrid orbital on one carbon and the other sp2 hybrid orbital on the other carbon. So since that overlap is falling right along the internuclear axis, that would represent one sigma bond. So that's part of our carbon-carbon bond right there. The other part of it's going to come from that unhybridized 2p orbital that has an electron in it. So each carbon has one of those. If we draw that, we're going to see that will look like just a p orbital with a node running through the axis. And they can overlap above and below. So we see overlap here and overlap here. This electron density lies above and below the internuclear axis. And so 2 electrons would come together, one from each carbon, and that would form one pi bond. Since we have that sideways overlap on hybridized orbitals, that's the only way we can form a pi bond is from the overlap of p orbitals. And lastly, we want to show our hydrogens overlapping. So each hydrogen has a half-filled 1s orbital. So here's a 1s orbital on hydrogen, another 1s orbital. We have 4 hydrogens, so there's going to be 2 more over here, 1s and 1s. Those are overlapping directly in one location. And so those electrons are going to become paired up. And each of those, since they're a single bond, is going to be just one sigma bond. So everywhere an sp2 hybrid orbital overlaps with a 1s on hydrogen, that simply represents a sigma bond, as we would have predicted just from looking at the Lewis structure. So our carbon-carbon double bond is made up of a sigma bond and a pi bond, and we have sp2 hybrid orbital overlap to form our sigma bond. Those run directly along the internuclear axis. And we had a half-filled 2p unhybridized orbital on each carbon atom that could sideways overlap in order to form one pi bond. And so this slide shows a little bit of a cleaner image of what we were drawing and going through, showing the sigma bonds and the pi bonds within the molecule ethene, which is C2H4. So over here on the left-hand side, the sigma bonds are showing those sp2 orbitals overlapping with the 1s orbitals on hydrogen. Same thing for the mirror image on the right. These are those sp2 hybrid orbitals, and here are those 1s orbitals on each of the hydrogens. The sigma bond in the middle is a result of that sp2 orbital overlap. And then we had, lastly, our pi bond, which those unhybridized p orbitals each had 1 electron in them this time, so they can overlap above and below the axis, forming a pi bond. And on the right-hand side, we can see kind of how that electron density spreads out above and below. It doesn't just stay separated like it looks like in our drawing. Those unhybridized p orbitals will spread out amongst the molecule to form that pi bond where there's that sideways overlap. Let's try another one. Use valence bond theory and hybridization to fully describe the bonding in acetylene, which is C2H2. So first we're going to start by drawing our Lewis structure for acetylene. We're going to have 2 carbons bonded together and 2 hydrogens on the outside. Hydrogen can never be a central atom. And so in order for our carbons to have a complete octet, we're going to end up having a triple bond between each of the carbons. So if we're going to end up describing a triple bond, we're going to have to describe a sigma bond plus 2 pi bonds. And then everywhere that there is a carbon-hydrogen bond, that's a single bond, so that would just be a sigma bond there. Once again, since there's no actual central atom, we can just pick one of the carbons and call it our central atom for now, and then the other carbon will be identical on the other side. So our carbon that I boxed in blue has 2 things around it. One thing is a hydrogen, and the other thing is a CH group. Therefore, our X shape is going to be AX2, and this will end up being a linear molecule, all falling in a straight line. The bond angles between everything in here are going to be 180 degrees apart since it is linear. So if we start by writing out our electron configuration for carbon, just as we did previously, we're going to have helium brackets 2s2, 2p2, and then it's helpful to look at our orbital diagram. So we have 2 electrons populating the 2s orbital and 2 electrons in our 2p. First, we're going to start by promoting one of our 2s electrons up to the empty 2p orbital. So we'll erase that and put that over here. And then we want to hybridize. Well, how many hybrid orbitals do we need to throw into our mix? Since it's an AX2 type molecule on our boxed in carbon, that means that carbon needs to have 2 equal energy hybrid orbitals. So what we're going to throw into our mix is 2 atomic orbitals. So starting with the lowest energy, that would be S, and then we'll use one of the p orbitals. We'll get out 2 new hybrid orbitals that are equal energy, and we'll call them sp hybrid orbitals. And we'll repopulate them with 1 electron each. And what we have left over this time is we have 2 unhybridized 2p orbitals that did not get thrown into the mix. So over here to the right, we'll rewrite those. We have our 2p orbitals, those are atomic orbitals, and they each have 1 electron in them. So now when we draw our orbitals on carbon and we show our bonding for acetylene, we're going to have 2 sp hybrid orbitals on each carbon atom and 2 unhybridized 2p orbitals on each carbon atom. That will allow us to show all of our sigma and all of our pi bonds in the molecule. So if we start by drawing our sp hybrid orbitals on carbon, carbon will be right here for one of them, and they're going to be 180 degrees apart. The other carbon is also going to have 2 sp hybrid orbitals. So we will have an overlap right here along the internuclear axis. And so that overlap is sp-sp hybrid orbital overlap. And directly along that axis we have 2 electrons that are going to come together and pair up. That will represent the formation of 1 sigma bond. That's only part of our triple bond right here. The other part is going to come from those unhybridized 2p orbitals that have electrons in them. So each carbon is going to have 2 2p unhybridized orbitals. So we can start by drawing one of them. That's pretty easy to draw. It's going to essentially be like a py, 2py unhybridized orbital. And that's going to overlap above and below the internuclear axis. That electron density will spread out. The electron spins will be paired. That's showing the formation of one pi bond. The other unhybridized 2p orbital is running on the z-axis. And so that's sticking straight out at us and going straight behind us. So we'll draw it on an angle so we can see this orbital. So this is representing essentially our 2pz unhybridized orbital. Each one has one electron in it. And so it's going to overlap above and below the internuclear axis, just like the last one. So that region of space will spread out. It's a little bit hard to see here, just because we're trying to draw in 3D on 2D. And this would represent our second pi bond in the molecule. Hydrogen, as before, has an electron configuration of 1s1. And so hydrogen will have that half-filled 1s orbital with one electron in it. And that's going to overlap right in the line at the end of the sp hybrid orbital on carbon, the other sp hybrid orbital. And so this region of space right here, the electron spins will become paired, and that will represent a sigma bond between carbon and hydrogen. And so when we look at our diagram, we formed a sigma bond directly along the internuclear axis, which was the result of sp hybrid orbital overlap on carbon. And also we formed two other sigma bonds that were the result of 1s and sp hybrid orbital overlap with carbon and hydrogen. And then we formed two bonds that were both pi bonds, and those were the result of either 2pz or 2py unhybridized orbitals overlapping sideways in two locations, and they are running perpendicular to our internuclear axis. And so that's the only way we can form those pi bonds, is when we have unhybridized p orbitals that have electrons in them and they can overlap. And so this picture diagrams the formation of our bonding in acetylene and describes it using valence bond theory. Here's a little bit of a neater picture than my own, showing that bonding in C2H2, we have our sigma bonds on the left and the right between our sp hybrid orbital and our 1s on hydrogen. So that region of space is running directly along the internuclear axis where it overlaps in one spot. We have another sigma bond from our 1s orbital overlapping with our sp on carbon. And then in the middle, we had our sigma bond, which was the result of sp hybrid orbitals overlapping, both of those on carbon. And on the right, we can see that electron density overlapping sideways to our internuclear axis, forming our two pi bonds. So we have one pi bond that we can see above and below the internuclear axis, and that would be the result of those two electrons coming together, their spins being paired in one of the unhybridized orbitals that is on each carbon. And then the second pi bond is going to be 90 degrees to that one, and it's showing it above and below the internuclear axis overlapping as well. And so anytime we have a triple bond, we're going to have one sigma and two pi bonds that have to be formed.